All right. So for the final part of lecture 1, we'll be discussing pass transistor logic. This is an alternative logic family. So essentially, kapatid siya ng CMOS, no? But they're not supposed to be used at the same time. We choose one or the other to implement a specific logic. So what is pass transistor logic? It's a multiplexer-based approach to logic. You don't know yet what a multiplexer is, so you'll find out soon. No? So, first, let's recognize that there is a problem with CMOS. Okay? In CMOS, we don't just have an R on. If this, so say for example, this is VDD, then this would have a low resistance, no? But it doesn't mean that this is completely off. In fact, there is an R off that is associated with a MOSFET that is turned off, no? So then this circuit would turn out not to have a zero current, but rather it will be consuming VDD divided by R off plus R on, right? And sometimes, especially in modern technology, this static leakage current is significant. And if you multiply that with VDD, then you find out, this consumes a lot of power, no? Multiply that across many trillions of gates nowadays in a single chip, then you have significant power consumption, no? So, introducing the idea of the pass transistor logic family, no? It's an alternative to CMOS, and it has two advantages. CMOS uses twice as many transistors, that is, you have N transistors for PUN and N transistors for PDN, while the PTL only uses N transistors because it only uses one switch network. No? Because of this as well, no, you'll see later that it has zero static power consumption. It's all dynamic. That is, the power is only used to charge capacitors and discharge capacitors. But the massive downside for pass transistor logic is that we have to refresh the voltage level after a while using a buffer every time. Okay? So, for example, this is a PTL implementation of an AND gate. No? So let's observe the behavior. So let's say we have A and B. If A, so let's complete the logic. If A was 0, no? So if A was 0 and B was 0, no? This was 1. 0 is shorted to Y. So Y is 0. Right? Next. Okay. If A is 0 and B is 1, well then Y is shorted to the ground, with the A, which is ground, so it's 0 as well. Right? Next. If A was 1, no, but B was 0, then this is Y being shorted to 0. So it's also 0, right? Lastly, if A was 1 and B was 1, then Y is now shorted to A through this top path, which turns it into a 1. No? And so, this is a very compact logic that implements the AND gate. Remember, we used 4 transistors for the AND gate in CMOS, but we used only 2 here. Okay? Next, we also have an XOR gate. No? So, you can observe here, if A is 0, then this is high, this is ground, no? And B is 0, so this is high, and this is ground. So then Y would be ground, right? Next, if B was 1, no, this would be high, and A is 0, then this would also be high, then Y would be shorted to 1, so it would be 1. Next, if A was 1, then this would be on, and B is 0, so this would be 1, then Y is also 1 because it's shorted to B, which is 1. Next, okay, if A is 1, then we choose the lower path, and B is 1, which turns this into ground, then Y is shorted to ground, which turns it into 0, thus completing the implementation of an XOR gate. No? So as a side note, I would like you to Google what an XOR CMOS gate looks like and compare it to this. No, it's a lot bigger. So, effectively, in fact, just two pass transistor logic transistors can implement a significant amount of logic. No, this is an exhaustive list of all of the possible logics that you can implement using just two PTLs. No, actually, it's not exhaustive yet because you can still make a multiplexer, but this is all of the two input logic that you can implement using just two PTL transistors. Okay. But PTL has a significant downside, no? One that prevents it from being used in computers, no? But it can be used in practical breadboard purposes and discrete, no? So the downside is that it has a voltage drop. So for example, here, if this was an NMOS, so you have an input VDD here, and you turn on the NMOS, no? The NMOS will have a voltage drop on the side that it's trying to drive, no? So if it was trying to drive this side, then this side will have VDD minus VTH, right? So then if that side had VDD minus VTH, then the voltage has already dropped. We no longer have VDD, right? So this is the highest that it can output, no? The good thing is that even if there's multiple transistors, so long as this part is VDD, that is the gate of the last switch transistor is VDD, then your output will only be VDD minus VTH. No, it won't go lower. The problem is that what happens if we put this here? Then it turns into VDD minus VTH, no? Which would need this to turn into VDD minus 2 VTH, right? So then, the PTS downside is a compounding voltage drop as you cascade logic, no? There are ways to manage this voltage drop, no? For example, we want to put in a complementary PMOS, which is kind of like CMOS already, for each switch. So what happens here? If we put VDD here, we want to put the opposite of that in the complementary PMOS, that is 0 volts. So then, PMOS is known to carry a strong VDD. The PMOS doesn't introduce a VTH when it's trying to carry across a VDD, no? So, the PMOS is the true path for this circuit, no? And in fact, this circuit combination, an NMOS and a PMOS, trying to pass a signal from its input to an output, is known as a transmission gate or X gate. All right? And it's used to carry analog signals through. Now, the other solution is to use a swing restoring inverter. That is, when you have a VDD here and you have a VDD here, the output is expected to be VDD minus VTH as talked about earlier, right? Unless we have an inverter here. So what does the inverter do? This one is still considered logic high. So then this goes to 0. But if this goes to 0, this PMOS turns on and charges this up to VDD. And now we have the VDD back. Now, what is the downside of this? This consumes static power now. What consumes static power? The inverter. Okay? So the inverter is a CMOS device. No? So, that is it for lecture 1.